Today's presentation will be focusing on some recently proposed solutions for accelerating deep neural networks for both image and video recognition. As transformers became the go-to architecture, claiming the long-held crown by CNNs, firstly, we'll be looking into ways we could mitigate the cost of their core components, the attention mechanism, in vision transformers. Then we'll briefly look on an orthogonal and general direction for model acceleration using extreme low bit quantization. So despite their unrivaled accuracy, running state-of-the-art models is slow and expensive in the cloud and impractical due to computational constraints and limited battery life on mobile devices. All in all, the deployment of neural network faces practicability and cost issues across the stack. Being a long-standing problem, the community embarked on a multitude of directions in an attempt to elevate this. A few prominent ones that we can mention are network architecture search, where the goal is to identify the best network topology formed by following a set of constraints defined by a user-constructed search space. While this is promising, their performance is highly correlated with the quality of search space. Searching with expanded, unconstrained search spaces is currently prohibitive. Moreover, in practice, the most popular adopted architectures remain the handcrafted one, where most of the architecture innovation, to say so, happens in practice anyway. Then we have network compression that attempts to either reduce the network size and accelerate its inference by pruning, where the goal is to remove the least important channels, sparsification, which attempts to learn sparse presentation or using matrix and tensor decomposition that exploit various forms of low-rank structures. We also have conditional computing, where it generally adjusts the network topology dynamically within a supernetwork, but it can also take various other forms, such as early exiting and so on. And finally, network quantization that proposes to perform the operations using data stored on a fewer number of bits. This allows for significantly smaller models and faster inference. In the extreme case called binarization, the multiplications can be replaced with bitwise operations. As we mentioned earlier, we'll primarily focus on designing optimized architecture and towards the end of the presentation, a bit on quantization. So, efficient transformer models. Transformers' general modeling capabilities came generally from two main aspects. So on one hand, they can be seen as performing on some sort of a graph, where the graph is fully connected, and the relationship between nodes can be learned in a data-driven way by optimizing against certain loss objectives. Transformer models, therefore, are highly versatile because any concept, whether it's a concrete one or an abstract, can be represented by nodes in a graph, and the relationship between these concepts can be characterized by graph edges. On the other hand, transformers have a good generality by establishing the relations between these graph-like nodes through a philosophy of validation. So no matter how heterogeneous the nodes are, the relation can be established by projecting them into an aligned space to calculate this similarity. On contrast, the convolutions depend heavily on their inductive bias, which is locality primarily and the weight sharing. So unlike CNNs, which gradually build the representation from lower to higher level features, where, for example, the initial layers just learn some sort of edge detectors and so on, transformers model the relation globally at each and every layer. This is easily spotted by looking, for example, at the gram matrix that shows the uniformity of the information learned across layers. Basically, what we can see here is that across all layers in a transformer, the features are somewhat similar. So even between the first and last layers, the features are not vastly different. While for ResNet architectures, there seems to be quite a bigger gap. Moreover, their formulation allows for an easy multimodal learning, partially enabled by the first point, as we can jointly process multiple modalities jointly. Hence why there is now a plethora of works that combine both text, audio, and vision data all together within the same input. However, their strengths are also their weaknesses. Lacking an inductive bias means that we generally need more data and longer training so we can learn these kind of relationships. While at the same time, attention operation is computationally heavy as it considers every possible interaction between the tokens at each and every layers, as I was mentioning. So to tackle these disadvantages, the most prominent directions that we could mention perhaps are sparse approximation, matrix decomposition, and there is also a gradual shift toward reintroducing domain-specific inductive bias. For example, if you look at Longformer, which proposes where the authors propose to perform a sliding window attention for all the tokens and global attention for a few selected ones, showing strong results for very long sequences of data, reducing the big O complexity from n squared to n. We also have Nystrom-Former, which tries to reconstruct the self-attention softmax matrix using a set of landmark points called Nystrom point, hence avoiding the direct computation of the n by n self-attention matrix. Other works focus on reintroducing domain-specific biases. For example, in Uniformer, the authors advocate for use of convolutional layers in the beginning and transformer layers towards the end, while models such as Swing Transformer add back pyramidal-like structure consecrated by CNNs and the sliding windows kind of mechanism. All in all, this sort of approaches significantly improve upon the vanilla vision transformer data and compute efficiency. However, despite all these improvements, when constraining the budget under, let's say, 2 gigaflops, vision transformers underperform current efficient convolutional neural networks, with modules such as EfficientNet and their follow-up, EfficientSV2 and so on, taking the efficiency crown. Another thing to note is that the number of flops doesn't really tell the full story, as the final latency can vary widely between different architecture despite similar flop count, especially across devices. For example, some components may be well suited for single-threaded hardware, while others can massively benefit from parallelization. A perhaps notorious example of this is the performance of depth-wise convolutions, which, especially early on in their adoption, had much better scaling on mobile devices compared with high-end GPUs. Therefore, it's not sufficient to consider this as the sole metric. Instead, from a practical point of view, ideally, we would want to also measure the inference efficiency in terms of latency and also energy consumption too. Moreover, while the model size constraint has been somewhat relaxed significantly, given the availability of ever cheaper and larger storage spaces, nevertheless, we should also be taken into account, too, as it often correlates weakly with the runtime memory. Finally, implementation threadless is also critical for model deployment, since standard operations are usually well optimized and supported across various different frameworks. So thus will not need costly per framework specialization. So guided by these principles, in our recent work titled EdgeVit, we propose a new local hierarchical pyramid attention block that can significantly improve the efficiency of vision transformer in terms of latency, flops, and energy consumption. Moreover, the proposed block consists of commonly used operations, and hence it's really easy to implement and support, and this can be supported easily across all major platforms. So as images have high spatial redundancy, applying attention to all tokens, even in a downsample feature map, is inefficient. There is hence an opportunity to reduce the scope of the tokens while still preserving the underlying information flow that model the global and local context. In contrast to previous transformer blocks that perform self-attention at each spatial location, our LGL bottleneck only computes self-attention for a subset of the tokens, but enables full spatial interaction as in the standard multi-head self-attention. So to achieve this, we decompose the self-attention into consecutive modules that process the spatial tokens within different ranges. So we introduce here 3 efficient operations: the local aggregation that integrates signals only from local proximate tokens. Then we have the global sparse attention that models long-range relations among a set of delegate tokens, where each of them is treated as a representative for a given local window. And finally, we have a local propagation that diffuses back the global contextual information learned by the delegate to the non-delegate tokens within the same window. Combining this, our LGL bottleneck enables information exchanges between any pairs of tokens in the same feature map at a low compute cost. So looking closely at each operation, we can see that for the local aggregation for each token, we leverage depth-wise and point-wise convolution to aggregate information in a local windows with a size of k by k. The global sparse attention, for global sparse attention, we sample a sparse set of delegates tokens distributed evenly across the space, where one token is selected for each R by R window. We then apply self-attention on these selecting tokens only, which is distinct, for example, from prior work, where all the special tokens are involved as squares in the self-attention computation. Finally, we have a local propagation where we propagate, as mentioned earlier, the global contextual information encoding the delegates tokens to the neighborhoods tokens using a transposed convolution. Note that the global sparse attention is composed of a special uniform sampler with, depending on where we are in the architecture, with a sample rank of 4, 2, 2, and finally 1. Because basically as we advance in resolution, we have a pyramidal kind of structure, so the resolution decreases, and we also adjust this sampling rate accordingly. The local propagation is implemented, as I was mentioning, with a depth separable transposed convolution with a kernel size and stride equal to the sample rate used in the global sparse operation. Here we compare a local aggregation operation to the locally grouped self-attention, LSA, in the leftmost part of the table, which is used in spin transformer. This validates our choices of using depth-wise convolution in local attention for local contextual learning. Then, if it's to analyze a global sparse attention, here we explore a few options for delegate token sampling, the maximum, the average, and the center. All choices perform somewhat similar in terms of accuracy. However, our default design choices, which you select the centermost token, is slightly faster. Finally, for the local propagation, we investigate two alternatives to the local propagation operations. First one is without local propagation, so we simply remove the local propagation. Note here that EdgeVit without local propagation has similar complexity to the standard EdgeVit. We're also trying with bilinear interpolation, where we use a bilinear interpolation pretty much instead of this transposed convolution to upsample the delegate tokens. And as we can see here, the effect of adding this component brings 0.5 points improvement. These numbers all tested with the smallest variant of the model, which has around 0.5, 0.6 gigaflops. On ImageNet, EdgeVit is significantly more efficient than all prior attention models, with the state of the art represented by the recent work of MobileVit, both in terms of flops, latency, and energy consumption. Perhaps more importantly, EdgeVit is the first to compare favorably against efficient convolutional neural networks. Here we're also showing a more in-depth comparison report, reporting timing, energy, power, and efficiency. For example, for energy measurements, we use a Monsoon high voltage power monitor connected to a Snapdragon 888 hardware development kit to obtain accurate power readings over the course of running a forward pass of each test model 50 times. The same torch script runtime is then used as in latency measurements. From the power signal reported by the monitor, we can then derive the average per inference power and energy consumption by first subtracting the background power consumption, and then identifying the 50 continuous regions of significantly higher power draw. Each region like this is considered as a single inference, and then we calculate its total energy as the integral over the individual power samples. Analogously, we can also calculate the average power consumption by averaging over samples of the set. Our model consumes significantly less energy than the prior state-of-the-art MobileVit and compares favorably with efficient ant models too. Similar results can be observed for image segmentation and object recognition too. Concluding on this part, the proposed EdgeVit architecture and its efficient attention block offers for the first time a viable transformer-based alternative to the convolutional networks in the low compute and power regime. Moreover, our work investigates in depth the power and latency characteristics of the proposed model and its immediate competitors. Code is available at the following URL on GitHub. Moving on from the image to video domain, where transformers also quickly establish themselves as a go-to approach. Here we'll argue that one, local attention generally approximates well the global one, and two, we'll look into proposing an efficient hardware-friendly approximation for it. In a sense, we are taking a step back from the global paradigm consecrated by the transformers. So as a very brief introduction, the goal of video recognition is pretty straightforward. Given a video stream, we want to identify the action occurring in it to get a better understanding of the user action, context, or environment. The two main approaches from an architecture point of view, at least traditionally, was either to use a 2D or a 3D network. The 2D-based processes each frame independently and then aggregates the information in the end. Examples of such models are, for example, TSN. In contrast, the 3D ones attempt to learn an explicit temporal relation within the network directly, creating interactions across time and space. However, these methods tend to be noticeably slower, although there are exceptions such as, for example, X3D. Beyond this, the community tried various combinations of the two, starting from literally using 2D and 3D convolutions across the network, using approximations such as 2D plus 1D convolutions. More recently, we can observe the same shift noticed in the image for image recognition, where the convolutional networks are gradually replaced with transformer-based architectures. The main gist of here is, of course, to take advantage of the multi-head self-attention mechanism. For example, in Transformers, Bertasis et al. Explores the effectiveness of transformers for video recognition, where we explore three main options: using spatial attention, which is equivalent to the 2D case mentioned earlier, but looks at relations within each frame separately. Then we have joint spatial temporal, where attention is performed across time and space simultaneously. Well, besides the temporal relation, it is expensive to compute and explodes in computation as the number of frames grows. Generally, making the model scale as the number of frames grows is one of the main challenges. Finally, the divided spatial temporal attention proposed in their work performs the spatial and temporal attention separately, as the name implies. While more efficient than the prior direct solution, this remains prohibitive to run as the number of frames increases. Now, to better understand the computational implication and visualize the interactions between patches across time and space, we illustrate here the interactions of a given token. In all cases, the key location of the query vector, located at the center of the grid in red, attempts are shown in orange. To combine the best of the world, we propose a new approximation to the space-time attention, and as the figure shows, unlike prior work, our key vector is constructed by mixing information from tokens located at the same spatial location within a local temporal window. Our method then performs self-attention with these tokens. Note that our mechanism allows for an efficient approximation of a local space-time attention at no extra cost when compared to spatial-only attention model. So, how it's done in practice? If is to have another look at how the multi-head attention works. So normally, this operation projects each input token initially constructed by taking non-overlapping patches from each input frame or image to three set of tokens called queries, keys, and values. The query and keys tokens are then multiplied together to form, after softmaxing, an attention map that is then used to scale and attend to the value tokens. If to look into the 2D case first, a direct natural expansion is to repeat this operation t times, one for each frame, and then aggregate at the end of the network the predictions made at the frame level. While fast, the obvious downside is the lack of interactions across time. Moving one step further, we can add space-time interactions by looking at all tokens across all frames jointly. Notice that this increases the complexity quadratically with respect to t. So ideally, we'd want to preserve the computational benefit of the former space-only attention while retaining the representation benefits offered by space-time attention. To achieve this, we make first an approximation to perform full space-time attention by restricting it to a local temporal window from -tw to tw. While at a layer level, this is enabled to learn a global relation. By repeating this operation at every layer, gradually we can form a temporal receptive windows that will cover the entirety of the input video. Effectively, we will switch from a global view to a local one once more. This reduces the complexity with respect to the time from t² to t multiplied with TW plus 1. As the number of frames increases, it becomes obvious, however, that such an approximation will result in faster models. Going one step further, instead of performing the attention between each token within the time window TW, we can pull information from neighboring frames and swap a certain number of channels between them, both in the forward and backward direction. In turn, this will allow us to perform interactions across time using only spatial attention. In practice, this channel swapping can be implemented by effectively shifting the appropriate channels, which is also known as a shift trick and incurs no additional flops, just some memory movement. When measured on a modern GPU, the cost of this memory will be negligible. As a result of this final approximation, the complexity of a space-time attention is reduced back to that of a spatial attention, which is T multiplied with S squared. For the overall architecture, we use the VAT model as introduced by the Savitsky et al., but inside our approach is plug and play and compatible with virtually any other vision transform architecture. Our final ingredient is the final aggregation for obtaining the actual predictions. To this end, we propose to consider the following options. A, to have a simple averaging module. So we'll just take an average over the temporal dimension. However, an obvious limitation of averaging is that the features are purely treated as an ensemble of per frame features, and hence it completely ignores the temporal ordering between them. To address this, we propose to use a lightweight temporal attention mechanism that will attend to the T classification tokens. In particular, the final token will attend to the sequence using a temporal transformer layer, and then this will be fed to a final classifier. A consequence of this, because we're attending only to these tokens, it means that the complexity of our layer is the bigger complexity of the layer is T, since it does not depend on the spatial tokens. When evaluated on the something V2 dataset, the use of temporal aggregation module offers around 2% boost in accuracy at little additional cost. Paramount to our work is the proposed space-time mixing attention, which is implemented by constructing a combined tokens across a temporal window via channel indexing. Space-time mixing rule can be applied in several different ways in the model, theoretically. So for completeness, here we study the effect of a space-time mixing for various combinations of a key value and to the input token prior to the KQV projection. As shown in the table, the combination corresponding to our module with space-time mixing applied to the key value significantly outperforms all prior variants by up to 2%. This result is important as it confirms that our model derived from the proposed approximation to the local space-time attention gives the best results when compared to other arbitrary possible variants. Altogether, it boosts the top one accuracy from 56.6 to 64.4. In terms of performance, our work matches and outperforms the state of the art at the time, while being significantly more faster. Here we have some results, for example, on Kinetic 600 dataset. Moreover, to showcase that the desirable properties offered by the proposed attention approximation translates well across model sizes, we evaluate the accuracy on a set of models in which the backbone is varied from VAT tiny to VAT large. As the table shows, our method results in high-performing, accurate models across the entire spectrum. To conclude on this part, the proposed approximation matches and outperforms prior work, will be significantly more efficient thanks to its linear complexity with respect to the number of frames. This suggests that global attention is not necessarily the key enabler of a transformer model. Coded models can again be found on GitHub by following this URL. Now, our previous discussion somewhat highlighted that global attention or even attention in general may not be necessarily a strict requirement for training highly accurate models. And the fundamental question of what really makes a transformer successful became the object of interest in a number of works. For example, in Metaformer, the authors ablated the effect of different types of token mixers, the global attention, special MLPs, and simple pooling. Perhaps surprisingly, the best performing variant was the pool former, where the authors simply replaced attention with pooling. This combined with the recent work titled Resonant Strike Back, bring empirical evidence that suggests that the success of a transformer, at least for a vision domain, largely comes from its overall architecture instead of a keeps token mixer and training strategy, where the transformers were typically trained a lot longer than the typical schedule for a resonant, which was typically 90, while for transformers, the general schedule is to train for 300 epochs. So building up on this idea,
Adrian. So just to, yeah, in these slides, so the pooling here, do you mean like they do max pooling or average pooling?
They tried both of them. I think in the end they went for average pooling.
And such a simple method works the best among these.
In terms of exactly. So in terms of so for similarly sized models in terms of flops, they will get higher numbers just by using pooling instead of attention.
Okay, I see. Thanks. Yeah.
So building up on this idea and the prior success of approximating local temporal attention with shift-based operations, we look on how we could expand this idea to fully replace the space-time attention. A direct extension is to perform only local attention, which in turn will be further approximated with channel swapping. Essentially, instead of shifting the channels across time, we will perform the shifting across width and height too. Note that different subsets of channels will be shifted across each of these directions. While this works reasonably well within 2 to 3% of the original accuracy of attention-based mechanism, it doesn't fully match it. Taking a look again on what the attention operation does, we can observe that it both mixes and rescales the tokens jointly based on the values of attention. In contrast, just swapping channels around along this axis only addresses the token mixing part, but it doesn't really emulate the rescaling. As such, to compensate for this discrepancy, we add a dynamically computed scale and bias. The scale is computed on per token basis, while the bias on a per channel one, effectively having some sort of a rank one approximation of the full position-wise rescaling matrix. In practice, the dynamic factors are computed using depthwise convolution, respectively a pooling layer followed by a linear projection. Both operations add insignificant overhead when compared with the total computational budget. Note that we also carefully preserve the overall architecture of the transformer models, including the projections from with the WV and WP weights. Here we show some results on something with two dataset again. As it can be noted, the proposed attention-free model, highlighted in light green, outperforms our prior transformer-based methods and largely match out the concurrent line of work from Uniform that uses a mix of convolutions and attention layers. Moreover, when applied for image recognition again, such approximation based on a shift with dynamic affine rescaling outperforms all prior attention-free transformers like models. Note that here we focus mostly on smaller models, but similar conclusions hold for larger ones. Concluding on this part, we can note that attention, at least in its global form, is not quintessential for high accuracy. And there are other forms of token mixers that can be used in their place without compromising performance. And perhaps even more importantly, we can actually improve the performance of the model by using different forms of token mixing, at least for the image and the video domain. And such models are typically more hardware friendly, as we don't have, for example, to form a large attention matrices and so on. With this, we kind of bring an end to the part of the presentation focusing on creating efficient transformer-like models. In the remaining part, we'll have a brief look on two low-bit quantization techniques that are somewhat orthogonal to the above directions. So before talking about what quantization is, let's have a very brief look on how numbers are stored in a machine. This slide mostly focuses on data stored in 32 or less bits, since it's pretty uncommon to use deep learning model of 32-bit precision. As you probably all know, we can either represent the numbers using fixed point representation or floating point. The floating point one representation is generally more advantageous since it allows for a significantly wide range of numbers to be represented. The structure typically represents 1 bit for the sign, depending on the type of representation. The rest can be then divided between the mantis, also called the fractional part, and And relatively recently, the community realized that networks can be in fact trained with lower precision, such as FP16 and so on. So so if we look at all of these numbers here, we can notice that as we are dropping the number of bits used to represent the numbers, we also significantly reduce the amount of energy and compute required really to both implement that operations and to process it. With the extreme case, requiring a few order of magnitudes less energy than the full FP32 or even really FP16 multiplications. In this part of the presentation, we'll mostly focus on the most extreme case, which is called network binarization, where the data is represented using a single bit. Such quantization allows us to replace all multiplication inside the binary convolution with bitwise operation. As a result, binary convolutions are up to 64 times faster and 32 times smaller on modern CPUs, with even higher peak performance achievable on FPGA using custom implementation. Note that these speedups come at large drops in accuracy whatsoever, at least generally, and bridging the gap remains somewhat of an open research question. It's also good to know that the quantization function of choice for binarization is the time function for both weights and activations, although there are variations, of course. So given these nice properties, why we don't see such networks used everywhere? Well, intuitively, training such networks is not necessarily straightforward, and it largely, as I was mentioning, remains open to research. Most of this difficulty arises from the discrete nature of the binarization, with gradients being uninformative that can either fade or explode. There's also high sensitivity to distortions, since small changes can make the jump between the two states. In a recent work called Expert Binary Networks, we look into alleviating this accuracy gap from 3K perspective. We firstly know that binary models have limited capacity, and as such, to increase it at little to no additional cost, we propose for the first time to combine and adapt a conditional computing to binary networks, introducing the expert convolutional network that at runtime will select one single appropriate expert. Then, to increase the representation capacity further, we increase the width of the binary networks while preserving the number of operations constant, generally using grouped convolutions. Finally, we design a set of expansions, directions that identify promising binary architectures. Our approach sets a new state of art for binary networks and reach an accuracy of 71% on imagenet without increasing the computational budget on a model size of similar to ResNet 18, albeit, as I was saying, this ResNet 18 will be divided by pretty much 32. So the proposed expert binary convolutions consist of a gating function and a set of expert weights and the convolution operation itself. The gating function is implemented using a small linear layer, followed by a winner take-all activation that selects a single binary expert out of a given set. The derivative of the activations is adapted such as that all weights will receive gradients during training, even if they were not selected. On the right, for a model with 4 experts, we can see that the network developed preference for certain classes of objects, evidentiating the effect of the multiple experts. Note that since the gating function is very light, the additional number of flops is insignificant. Beyond this, we will also make some architectural tweaking, such as extra skip connection, increase width, and group binary convolutions to further improve the model power. So unlike full precision networks, binary ones can represent a finite, relatively small number of unique combinations. So to increase the information flow carried by the features, we can either increase the number of channels or the kernel size. Since the latter is dependent on the data and modeling, we focus on the former. However, since simply increasing the width will increase the computational cost too, we propose to make use of group convolutions. Note that depth-wise convolutions are not really friendly to binarize due to the so-called double approximation problem, where the depth-wise convolutions are already an extreme approximation of a normal convolution. So now we're going to do two extreme quantization, well, two extreme approximation pretty much on top of each other, and this tends to not go very well. Now, as our results show, increasing the number of channels and the group size jointly offers significantly accuracy gains, pretty much no extra computational cost. We also go beyond this and define a set of network topology directions and search along this line of an optimal configuration. Mainly there we explore the effect of distribution of layers across different resolutions. Surprisingly, we find that the particular arrangement matters quite little to the final accuracy. Then we can also analyze wherever deeper or wider architectures are better. Giving this the information on bottleneck, we find that deeper models, for example, wider models are generally better. Thirdly, we also analyze how it's best to aggregate the features after a grid convolution and find an additional one-by-one layer is generally required for optimal performance. Finally, we also analyze how many groups should be used and how they should be distributed. And then we combine all of this together in some sort of semi-automatic network architecture size procedure to find which of these combinations should be used and how. As the results in ImageNet show, we notably improve in terms of accuracy over prior work while maintaining the same performance advantages that consecrated binary networks. In the paper, we have a more in-depth analysis of all these components, and I invite you to check it for more details if needed. For example, here we see this kind of BOPS binary operation metrics. Typically easy way of converting them to equivalent flops. What people use is just to divide this number by 64, assuming 64-bit width long processor of data. Now, while binary networks are very efficient, they one require custom implementation for optimal performance, and two, they may underutilize powerful devices. Hence, we would ideally want to be able to determine the level of quantization per se of the model depending on the underlying hardware. However, quantizing or designing a model for each device in part can be labor intensive. Hence, instead of creating different models depending on the platform and capabilities, we look into creating some sort of a meta network that can offer fine-grained accuracy speed trade-offs. In the framework of network quantization, one way of adjusting the ratio between speed and accuracy is by changing the number of bits per network, block, or layer, which is what we explore in our recent work, but with the major modifications. Our proposed approach creates networks that can change their bit width at every block at runtime without extra training, such as to allow the same network to be suitable for multiple devices at once. Before moving forward, it's important to note that generally there are two types of quantization strategies, post-training and training-aware. In the first case, the network is quantized after the full precision training without extra training, just by performing a calibration procedure, while in the later, we have to do the quantization at train time. And while for a higher number of bits, post-training quantization is feasible, for 4 bits and less, typically we will need a training-aware quantization. Therefore, if you want to change the quantization level of a network, we pretty much have to retrain it or to fine-tune it further from that point. So given this, basically it's unfeasible to have directly such kind of network where we could change the quantization level at runtime arbitrarily. So the question is, what if we could define the quantization level instead per layer or per network? One direction that tried this at the network level is in ADA bits, where the authors elevate the storage issue and so on by training a model with n quantization level and shared weights. So for example, you will have one network that can be quantized all layers to either, let's say, 1 bit, 2 bits, 3 bits, and so on. However, you cannot have any other combinations between them. So with the capability of adjusting it at every layer, we can have some sort of a smooth transition between accuracy and speed, depending on device characteristic and so on. So to this end, to deviating from the common paradigms, we introduced the first network with granular bit width selection at runtime. Unlike prior work using a single shared set of weights, whose size is defined by the highest bit width at runtime, our method can select arbitrary combinations of different bit widths, allowing for a fine control between accuracy and speed without affecting the overall network ability for highly accurate inference. For the rest of the presentation, we'll refer to our proposed approach as BitMixer. In summary, in BitMixer, we propose the following modules and contributions. To properly compensate for the distribution shift that arises when a change in bit width occurs between two consecutive layers for each transition between different bit widths, we propose to learn a separate batch normalization layer coined transitional batch norm. Traditionally, different quantization schemes were used for 1 bit and 2 and n bit quantization. However, here we propose the shared formulation for both of them. Finally, since training such network is non-trivial, we devised a specialized training strategy that allows the training of such meta networks. And then we analyzed how we could select or sample subnetworks or network configuration out of this model. Our unified quantization scheme attempts to address two prevalent issues. So firstly, different functions and formulations are used for 1 bit, as I was mentioning, and n-bit quantization. The n-bit quantization is typically performed using round operators, while binary one using sign functions. Secondly, quantizing to n-1 requires a full precision weight, since the level between quantization layers don't really match, as we can see in the leftmost figure. As such, instead, we operate directly on the plus-minus MB range for all quantization types, using a floor function, aligning the quantization levels as shown in the rightmost figure. So now we can directly, for example, obtain the 2-bit quantization from the 3-bit one. Now, quantizing the individual layers and blocks to different bit widths will result in features that follow different distributions. This is a consequence of the inherent change in representation power due to the change of precision and the fact that the network is unable to approximate closely the feature distribution of higher bit widths. To properly compensate for this, for each transition between different bit widths, we propose to learn a separate statistics for the batch norms, coined transitional batch norm. We know that introducing these transitional batch norm layers does not induce any increase in the complexity of the network, and there's only a small increase in the network size due to this additional set of parameters. Importantly, we emphasize that without this, the network is unable to really converge to a satisfactory level of accuracy, as we can see in the bottom right corner. Notice also the reduction in average variance before and after in the figure shown. A key remaining aspect is how to train the proposed meta network. A direct naive approach where all the paths are active simultaneously is unfeasible due to both memory and computational constraints. Besides this, we considered an approximation to this training where all active paths are considered between two adjacent layers. Even in this case, we found that models was unstable to train due to the internal competition arising, especially earlier in the training. A more computationally feasible approach is to randomly select with equal probability during training an active subpath or set of active subpaths. However, this leads to networks where all paths have similar accuracies. So in our approach, we firstly warm up the network without randomized bit widths during the so-called stage 1 and 2. Then, to obtain the final meta network, we progressively train the previous models, gradually transitioning from networks where all the layers are quantized to the same bit width to ones where the quantization level is randomly selected at a block or layer level, which happens in the stage 3. Now, the BitMixer trained meta networks contains an exponential number of subnetworks, and by changing the bit width of its individual layers at runtime without any extra training, we can obtain fine trade-offs between accuracy and speed. However, not all subnetworks are created equal, and as such, it's interesting to identify the most promising candidates. This can be viewed as a post-training network search. To facilitate the selection of interesting candidates out of a given population for each layer, we compute the top eigenvalues of a Hessian. In general, smaller eigenvalues correspond to flatter loss surfaces, which in turn suggests that such layers are good candidates for more aggressive quantization, given that the induced errors are less likely to be amplified. Then, giving a target cost, we generate a set of candidates using greedy approach and rank them accordingly to the cost computed by the eigenvalues. The best models are then selected and evaluated. On the right, we can see a few subnetworks plotted out of a single model. Notice here the gradual transition and the gradual trade-off between the average bit width, which correlates with the speed of a network, and the top one accuracy as measured using a ResNet 18 size model on imagenet. Here we can see some additional comparison against other bits. The baseline that I was mentioning that trains a model that can be quantized can quantize the entire network to the given bit width, and add MIPS, which tries to automatically identify the bit width of the layers. Note that only our method can select the bit width per module at runtime. With this, pretty much my talk concludes. So today, what I was trying to present as a main idea is that we looked into how we can take attention and make it more efficient, trying to bring, so because the transformers already work very well in the high compute budget, so we try to see ways of bringing transformers to the lower compute budget. So there we focused with the EdgeVit on how to make transformers particularly efficient in the below 2 gigaflops range, focusing also on some practical aspects of this, which was to also take into consideration the energy consumption, the latency, and so on. Then we giving that it appears that transformers, at least the key component of transformer performance, is not coming from attention, or at least not in its global form. We are looking for alternative ways alternative efficient ways of mixing the tokens for both video and image recognition, trying to create models again that are extremely efficient across both scales. And this is particularly important for video data, where we are having a larger number of tokens, since we have special tokens of each image multiplied by the number of frames that we're trying to process. Finally, we looked into some quantization techniques, where the idea is with the right approaches, by using, for example, the proposed architectural variations and the proposed combination of conditional computing with binary networks, we can get very fast models capable of running on really low power devices. And finally, we looked into making this kind of quantization even more flexible by having a model where we could change the quantization level of a given layer arbitrarily at runtime. Here, if you want to check more, I'm also listing the papers that I talked about. And yeah, if you have any questions,